If my derivative is negative, that implies f of x is what, Jonathan? Decreasing. If my derivative is increasing, that implies that my original function is what, Julia?
Concave.
Concave up.
Here, this is for you, Miss Eric.
Thank you. Who else needed one? Do you really need one? Do you really need one? Okay. If you have something. I wasn't sure if you were just making a fashion statement or something. All right. So, Kushbu, what about f prime of x is decreasing? Concave down. All right. So if my derivative doesn't exist or my derivative is equal to 0, that means what, Kavita? X is a critical point, so we have a critical point at x. I think these other ones I need a bigger one now.
I printed out before you put it out. Me too.
All right. So f prime of x is 0 and it's increasing means what, Andy?
There's a critical point.
Very critical. You also have to use the fact that it's increasing there.
It's a relative max.
No.
Oh, relative min. Okay. If it's increasing, that means it's concave up. And if it's concave up, that's a relative min, right? The minimum is the y value. The relative min occurs at x. So if I said, where's it at? I'd say at x. What is the minimum? It would be the y value. So Justin, over here, Justin. F prime of x equals 0 and it's decreasing.
Relative max.
F of x is a relative max, sure. Okay, Justin 2. F prime of x is a relative min or a relative max means what? What happens when my derivative is a relative min or a relative max?
It's concave up or down.
No. Huh?
Inflection point.
No. Remember, I'm asking you to describe something in my original function.
Oh, my arm is getting tired already.
Poi. Do you know what poi is? It's not
boy.
It's not the. It's not the pudding that you get in Hawaii. Poi. Point of inflection at x.
I'm recording. What do you think?
Like Michael's big head. That's
Because look, right here, that's a relative max, right? What's my function doing here? It's increasing, which means I'm concave up. What's my function do after my maximum? It starts decreasing, which means it's concave down. So I've changed from concave up to concave down, which means point of inflection. In fact, if you go back to my definition of a point of inflection, the definition was that's where my derivative changes from increasing to decreasing. Right? But I kind of phrased it as it's the location where we change concavity. Are you taping me right now? Just do my voice. Don't get like.
Don't worry, mister. I didn't zoom in.
Really red is
It's always red. I'm outside too much.
I like your tan.
You like my tan? I don't know if it's considered a tan. It's just like a burn.
Shirt bit.
Your t-shirt tan?
Yeah,
your
your
t-shirt
Oh, my t-shirt tan? I got a tan on my socks too. My sock line. It's like a farmer tan. All right. So what we're going to do next is you're going to give me the interval. We're using this graph right here. So we want to answer over what interval is f of x increasing. So Sean, why don't you give me that one?
negative infinity to.
No.
That's the F primitive.
I don't want you to describe when this is starting.
5 to 0 and 40.
3.5 to infinity. Because it's crossing between 3 and 4. Not the same thing. But close. Just make sure we examine
This is
this.
Sean.
All right, what about decreasing, Sophie?
What, from negative infinity to negative 5, and from 0 to 3.5.
0 to 3.5, sure.
When you hanging? When you hanging?
Oh,
F of x is concave up over what interval, Jonathan?
Negative infinity to negative 3.5.
Let's just say negative 3.
Okay, and 2 to positive infinity.
Yep. Maybe I should just.
Ouch. Oh, Sophie just poked me.
oh, your hand is.
And concave down in what interval? So harsh.
No, negative 3 to.
Hey, Krista.
Negative 3, 2. F of x has a local maximum where, Tanya?
At negative 5, 0, and 3.5.
Remember, we don't want to give the point here. We wouldn't want to say negative 5, 0, because that's not really a point on my original function.
Oh, no,
What's the only coordinate on the original function? Okay, so let's talk about a relative maximum. Maximums occur when the concavity is what?
Negative. Or decrease. Or down.
Down, which means my first derivative has to be doing what?
Decreasing.
Decreasing, right? So look at that graph again, and what would the answer be? Just a 0, sure.
Wait, isn't it supposed to be from like positive to negative?
What?
Isn't it from positive to
That's where it's
negative?
second derivative. This is first derivative.
Okay. What's this?
What?
Positive? What's that?
Negative.
Negative. So yes, that is a correct statement. But that's where it goes from positive to negative. Okay? So you see? So I mean, honestly, what I would do when I approach these problems, when it says I want a maximum, I would think, okay, a maximum occurs where the derivative is 0 and where I'm concave down. What's concave down mean? It means my derivative must be decreasing. So I look, where's my derivative 0 and decreasing at the same time? And that would be that point right there. Okay? So try to translate the whole statement into things in terms of the first derivative, and then look at your answer. Because otherwise you're going to be tempted to say one of these guys here, because you just look for where it's 0, and then without really thinking about the concavity. All right, so Andy, what about the next one? Local minimums at x equals what?
X equals negative 5 and 3.5.
Sure. And then our last one is going to be f of x has points of inflection at x equals negative 3 and x equals 2.
Wait, so does it mean that whenever it's decreasing, it's a relative mass?
It's got to be decreasing and it's got to cross the x-axis, meaning it's got to have a derivative equal to 0. Now remember, these little rules that I'm giving you are for like nice, neat. If you remember that what it said in the very top, it talked about functions that are continuous and differentiable, both the first and second derivative. When we start getting functions that have cusps, then the derivative doesn't exist at those points, right? And these things, so I mean, these statements right here are always true, but relative minimums and maximums can also occur where the derivative doesn't exist too, right? And those are kind of like the special cases that you have to think individually. But if it's a nice, neat curve, these things work perfect. Okay? And honestly, I mean, if you have something like this, even if it's a curve or just a sharp turn like that, if that was the first derivative and it's a sharp turn like that, that's still a place where we change from increasing to decreasing, right? Which means we change concavity. So even though it might not be a smooth curve and the next derivative doesn't exist there, it's still going to be a point of inflection. All right. And then just on the second side of this, I just had the following statements, and they were basically about the second derivative. The second derivative doesn't really give you as much information as the first derivative. It only tells you three things. It tells you concavity, concave up, concave down, and points of inflection. So if the second derivative is positive, we are concave up. If the second derivative is negative, concave down. And then finally for this one, if the second derivative is 0 and passes through the x-axis, then we have a point of inflection.